Hold on.
I forgot. Oh my god. John sat there and I was like, I knew it.
Okay.
3.08 seconds.
3.08. Okay, hold on. All right, next we got John Clark, who has a reach of 8 feet.
Straight up. See that?
All right, next we got Ryan with an initial height of 7 feet 5 inches.
Oh, okay. Oh, someone's an athlete.
420.
Why is that so exciting? Ern said 420.
Why are you still videoing me? Should I go?
Yeah.
Okay. Our original function was negative 16 t squared plus initial velocity times time plus initial height. And you said that equal to 0. So our greatest time was 4.2 seconds and our initial height was 7.5. So you plug that in. And then you multiply that out, it equals, oh, it's not. Oops. Can I restart?
Just keep going.
It's working. We get it.
Push.
I feel like Jonathan. And if you isolate all the constants to one side, you get 4.2. And you divide on both sides. You end up equaling initial velocity equals 55.414 feet per second. Oh, I'm out of it. I think I ran out of battery, but yeah. Whoa.
Okay, when the height of the ball is 0, the time corresponding to our function is going to be 4.2 seconds. This is the point at which the ball touches the exit intercept, or in this case, it is actually on the ground. Since Jacob solved our initial velocity to be 65.414 feet per second, we can come up with a general equation of negative 16 t squared plus 65.414 t plus 0.75 feet. Okay, at what time does the ball reach its highest point? And be sure to give units. Well, if we use the negative b over a, or 2a, okay, the ball is going to reach a max of 74.36 feet at 2.044 seconds, with of course the seconds being our x value, finding the vertex value, or our axis of symmetry, and plugging it back into our general equation and coming up with 74.36 feet, which was the height that Ryan threw the ball. Okay, for our second activity, we're going to take a normal piece of letter size paper and fold it into 3 equal parts, count the number of rectangles formed, and then fold the paper again into 3 equal parts and continue to repeat this process, recording the number of rectangles that our piece of paper is folded into at each stage. So if we start to do this, we're going to see a pattern here. And so what I did is at stage 0, we start off with our initial rectangle, okay, which is just one rectangle. But then if we fold it into 3 equal parts, you're going to see that at stage 1 we have 3 separate rectangles on our piece of paper. Okay, taking that same paper and folding it again during stage 2 is going to give us 9 similar rectangles, okay, congruent rectangles. And if we keep repeating the process, at stage 3 we're going to have 27 rectangles, and at stage 4 we would have 81 rectangles, and past this point it's rather difficult to try to fold the piece of paper into 3 equal parts anymore. So our table begins to look like this, and we could take a good educated guess that at stage 5 that we would have 243 rectangles if we were able to fold the paper into that, and so on and on it would go for n number of folds. So looking at the data in the table, there was a pattern to the number of rectangles formed as the fold stage increases. So describing that, we just say that the number of rectangles is growing by a multiple of 3, okay, at each stage. If we had to write a rule to find the number of rectangles formed if the paper was folded n times, well, with n being our fold stage, our rule would be 3 to the nth power is equal to the number of rectangles formed, and this would go on and on. It says predict the number of rectangles after 10 folds. Well, using the equation on the previous page, our equation just states that it would be 3 to the 10th power, which is 59,049 rectangles on that piece of paper. If the paper now has 6,561 rectangles, how many folds would you have made? Okay, well, since we're trying to solve for the exponent, we have 6,561 is equal to 3 to the x. If we change that to a log base of 3, 6,561, we can solve for x. Using the calculator, we have to enter it, because it's not a base 10, as log of 6561 over log of 3, and we would get 8. So at 8 folds, we would have 6,561 rectangles on our paper. If we make a sketch of the scatter plot, you're going to see that only after a few folds, just 4 folds, we're going to be off, and that's using the y-axis in a scale of 10. Okay, so we start out with our initial 1 rectangle, 3 rectangles, 9 rectangles, 27, and rapidly reach 81. Now, if we had to describe this, I would describe this as rapid exponential growth.